Electric potential energy U. Electric potential energy U. We can infer that the electrostatic force is a conservative force. Thus, when that force acts between two or more charged particles within a system of particles, we can assign an electric potential energy U to the system. If the system changes its configuration from an initial state I to a different final state F, the electrostatic force does work W on the particles. Delta U equals UF minus UI equals minus W. Here, W is the work done by the electric force. Okay. This is a definition of potential energy, right? We only define delta U. And this work should be independent of path because it's a conservative force. For convenience, we usually take the reference configuration of a system of a charged particle to be that in which the particles are all infinitively separated from each other, and we usually set the corresponding reference potential energy to be zero. Suppose that several charged particles come together from initially infinite separations I to form a system of nearby particles, state F. Let the initial potential energy Ui be zero, and let W infinity represent the work done by the electrostatic forces between the particles during the move in from infinity. The final potential U, delta U, equals minus W infinity. Here, infinitive means we set the U at the infinity is zero as a reference point. As is true of the other kinds of potential energy, electric potential energy is considered to be a type of mechanical energy. If only conservative forces act within a closed system, the mechanical energy of this system is conserved. We shall use this fact extensively in the rest of this chapter. Electrons are continuously being knocked out of air molecules in the atmosphere by cosmic ray particles coming in from space. Once released, an electron experiences an electrostatic force F due to the electric field E that is produced in the atmosphere by charged particles already on Earth. Near Earth's surface, the electric field has the magnitude E, 150 Newton per coulomb, and is directed downward. Question: what is the change delta U in the electric potential energy of an released electron when the electrostatic force causes it to move vertically upward, so a distance d 520 meters? This is the electric field of Earth, is towards the Earth. And this electron, it was absorbed a force by the E and move up. After move D, what is its potential energy change? We know F equal to W equal to F dot D. In this case, F equal to E. Okay, right. And this E, D is the same direction. Okay, this is E, this direction. Okay, these they are opposite direction. Okay, opposite, same line, opposite direction. So the angle is 180 degrees. So E dot D equal to ED cosine 180, and cosine 180 is minus 1. So W equal to minus, this is minus, two minus to get a positive. Okay, now, this is electric charge on electron, minus number. E is 150. D is 522. And cosine 180 is minus 1. 2 minus, we get a positive. Okay, we're going to, okay. 1.2 times 10 to the minus 14 joule. And by definition, delta U equals minus W. So I put another minus, the potential change is minus 1.2 times 10 to the minus 14 joule.